Okay, so number one, what does the Latin word scientia mean? Well, if we look back here, science is not just a subject in school, it's a method for studying the natural world. After all, science comes from the Latin word scientia, which means knowledge. So there's your answer to number one right there is knowledge. So number one is knowledge. Number two, what is science? Well, science is a process based on inquiry that helps develop explanations about events in nature. So that's your definition for science. That's number two. What is science? Number three, give two examples of rules that nature follows. So, nature follows a set of rules. Many rules, such as those concerning how the human body works, are complex. Other rules, such as the fact that Earth rotates about once every 24 hours, are much simpler. Scientists, such as the ones shown in Figure 1, ask questions and make observations to learn about the rules that govern the natural world. So, we have conducting water quality testing down here. Okay. So your answer for number three, two examples of rules that nature follows. You have a couple of examples here. So you have the rules about how the human body works or how any organism works. So basically how they digest food or how they make energy, etc. How muscles work. Another simple rule, Earth rotates about once every 24 hours. You could also talk about the Earth revolving around the sun once every year, or the moon orbits the Earth every 28 days, stuff like that. Those would be other rules you could use as examples. Number four, what are three major categories of science and what does each category study? Well, science covers many different topics that can be classified according to three main categories. You have life science, which deals with living things. You have earth science, which investigates Earth and space. You have physical science, which studies matter and energy. So there's your three answers for number four. So you have life science, you have earth science, you have physical science. And then here it tells you what each one does. Life science deals with living things, earth science investigates Earth and space, and physical science studies matter and energy. Okay, so again, that's number four. Sometimes, though, a scientific study will overlap the categories. One scientist, for example, might study how to build better artificial limbs. Is this scientist studying energy and matter or how muscles operate? She is studying both life science and physical science here. May also look at how nerves interact with this artificial limb and stuff too, if it's controlled by nerve impulses. All right, so science changes. So scientific explanations help us understand the natural world. Sometimes these explanations must be modified. As more is learned, earlier explanations might be found to be incomplete, or new technology might provide more accurate answers. So this gives us an answer then to number five. Can scientific explanations change? If so, what causes scientists to change their minds about explanations? Well, sometimes these explanations must be modified. So yes, scientific explanations can change. As more is learned, earlier explanations might be found to be incomplete, or new technology might provide more accurate answers. So that is the why. That's why they change their mind. We don't really change our mind. It's more the explanations we have are based on the best information available at the time. But for example, scientists have been studying the atom for more than 2 centuries. Throughout this time, they have revised their thinking on what atoms might look like and how they interact and even how they combine to form other substances. In the early 1900s, British physicist J.J. Thomson created a model of the atom that consisted of electrons embedded in a ball of positive charge. Several years later, physicist Ernest Rutherford created a model of this atom based on new research. As shown in Figure 2, his model was different from Thomson's model. Instead of a solid ball, the atom consisted of a nucleus with electrons orbiting it like the planets orbit the sun. Okay, so you have Thomson's model here. We have the electrons sort of embedded in this positive sphere. And then you have Rutherford's model where you have a nucleus and then the electrons kind of flowing around that nucleus. And now we have the present day model, which is the electron cloud model. So later in the 20th century, scientists discovered the nucleus is not a solid ball, but is made of protons and neutrons. This improved our understanding of the atom and its behavior. The present day model of the atom is a nucleus made of protons and neutrons surrounded by an electron cloud. The electron cloud represents the space containing rapidly moving electrons. The electron cloud model is the result of scientists pulling together evidence from many investigations. they came to an agreement that it is the best model for the information available at the time. And again, that's what scientific explanations are. They are the best model or the best explanation for the information available at the time. More information, though, better models. Because it is the nature of science to be open to change. Investigations into the model of the atom continue today. All right. So now we're down to number 6. Describe the two main types of scientific investigations. So investigations. Scientists learn new information about the natural world by performing investigations. Some investigations involve simply observing something that occurs and recording the observations. This is an observational study. Other investigations involve setting up experiments with a control to test the effect of one thing on another. These are experimental studies. So those are our two main types of scientific investigations. You have observational studies, where you just simply observe things and record those observations. Then you have experimental studies, where you actually set up an experiment and test the effects of one thing on another. Modeling. Sometimes an investigation involves building a model that resembles something, such as a model of a new space vehicle, and then testing the model to see how it acts. Other models represent processes or objects that cannot be seen with the unaided eye, such as the models of the atom. Often a scientist will use information from several types of investigations when attempting to learn about the natural world. Scientific methods. Okay, so our next question, number 7, what are scientific methods? So we have scientific methods here. Although scientists do not always follow a rigid set of steps, investigations often follow a general pattern. Now, the pattern of investigation procedures is called the scientific methods. Okay, so your definition for scientific methods is this pattern of investigation procedures. 6 common steps found in the scientific methods are shown in Figure 3, which is here. So you have state the problem, gather information, form a hypothesis, test the hypothesis, analyze data, draw conclusions, and then from there, if the hypothesis is not supported, then you may modify the hypothesis and then start over. If the hypothesis is supported, you'll repeat that several times to see if it continues to be supported. But a scientist may add new steps, repeat some steps many times, and skip steps altogether. And again, if you follow this, you're following one set of steps down to draw conclusions. Once you get to there, it depends. If your hypothesis was supported, you just keep repeating it. If your hypothesis was not supported, you got to go back and modify the hypothesis, or maybe even go back and gather more information. So you may have to go back up to here. Maybe even go back up to here, state the problem. There may be a new problem you discovered. So it's not one set of steps that goes from A to B to C to D to answer, Okay, so state the problem. To begin the process, a scientist must state what he or she is going to investigate. Many investigations begin when someone observes an event in nature and wonders why or how it occurs. The question of why or how is the problem. So that's what our answer to number 8 over here. What is the very first step in any scientific investigation, and how do many investigations begin? So the first step really is to state the problem. So you must state what you're going to investigate. If you come back up here, state the problem. Okay, you have to start with your question. What are you trying to answer? What's your problem? And then how do many investigations begin? Well, they begin with an observation of an event that makes you wonder why or how, and then that becomes your question. All right, so scientists once posed questions about why objects fall to Earth, what causes day and night, and how to generate electricity for daily use. Many times, a statement of a problem arises when an investigation is complete and its results lead to new questions. So a lot of good experiments and good investigations lead to new questions. For example, once scientists understood why we experience day and night, they wanted to know why the Earth rotates. Sometimes a new question is posed when an investigation runs into trouble. For example, some early work on guided missiles found the instruments in the nose cone did not always work properly. The original problem statement involved how to guide missiles during flight, and then the new statement involved how to protect the instruments in the nose cone. Now, research and gather information. So before beginning an investigation, scientists research what is already known about the problem. They gather and examine observations and interpretations from reliable sources. Again, reliable sources. Things that are published in professional journals and things like that. But this background helps scientists fine-tune their question and form a hypothesis. Okay, so that's sort of our answer then for number 9. Why do scientists research what is already known about the problem? Well, we research what's already known to fine-tune our questions and form a better hypothesis. Okay. A hypothesis is a possible answer to a question or a possible solution to a problem based on what you know and what you observe. That's our answer then for number 10. What is a hypothesis? Okay. Again, a hypothesis is a possible answer to a question or a possible solution to a problem based on what you know and what you observe. You may have heard this defined as an educated guess. Well, the educated part is this background research. So you research what's already known, that's your educated part of it. Then you kind of make a guess about what's going to happen. I would like to add that a hypothesis has to be testable as well. So you have to be able to test it in some way. But when trying to find better material to protect the space shuttle, NASA scientists looked to other materials that were used in similar situations. Scientists knew that a ceramic coating had been found to solve the guided missile problem, and they hypothesized that a ceramic material might work on the space shuttle also. Now, test the hypothesis. So some hypotheses can be tested by making observations. Like, for example, does this specific bird live in this area? Well, you go out and you look for it, you listen for bird calls, etc. Or does this type of tree or this plant live in this area? You go out and look for it, make observations. You can't really develop an experiment for that. But others can be tested by building a model and relating it to real-life situations. One common way to test a hypothesis is to perform an experiment. An experiment tests the effect of one thing on another using a control. Now that is our answer for number 11. What is an experiment? Well, an experiment tests the effects of one thing on another using a control. And then our next question, number 12, is what is a variable? And then we've got also what is a dependent variable, an independent variable, and then constants and a control. These are all here together. So variables, an experiment usually contains at least 2 variables. A variable is a quantity that can have more than a single value. Table 1 summarizes the types of variables. For example, numerous experiments aboard space shuttles and the International Space Station have studied the effects of microgravity on plants. Before these experiments could begin, scientists had to think of every factor that might affect plant growth. Each of these factors is a variable. So our answer for number 12, what is a variable? A variable is a quantity that can have more than a single value. Okay. Then some of our definitions we can get from this table right here. So a dependent variable, which is number 13, what is a dependent variable? Dependent variable changes according to the changes in the independent variable. Now, I like to also think about a dependent variable as dependent variable is a measured variable. It's an output variable. Okay, so it's something that comes out of the experiment, something you don't know going in. Okay, so think about the D at the beginning of that. So don't know at beginning. It's what you're testing, what you're trying to find out. So you don't know at the beginning what that dependent variable, what the answer is going to be. Now, the independent variable is the variable that is changed to test the effect on the dependent variable. Now, an independent variable you kind of think about as an input variable. Okay, think about the I in that. It's an input variable. You decide at the beginning. Okay, it's also a manipulated variable. You change it on purpose. So manipulated variable. All right, so we changed that one on purpose. Now, constant, so that's also our answer for number 14. What is an independent variable? So you could get that from here, or you could get that from here again. Input variable, decided at the beginning, manipulated variable. The dependent variable, number 13, you could go back up here, again, changes according to the changes in the independent variable. It's a measured variable, output variable. You don't know this at the beginning. And then a constant is a factor that does not change when other variables change. It's something you keep the same through all of your experiments. So 15, what are constants? These are things that do not change. A factor that does not change when other variables change. And then a control is a standard by which the test results can be compared. So that's what our control is down here, number 16. Okay. We're going to hit all these again here in a minute. But a control is basically like the status quo. It's what's normally done, or if you're talking about like a fertilizer or something, like testing fertilizer on plant growth, maybe it's no fertilizer, as an example. Or if you're talking about the gravity experiments down here, well, normal Earth gravity would be our control. So, independent and dependent variables. So, in the microgravity experiment, plant growth is a dependent variable because its value changes according to the changes in other variables. So, we're measuring this. This is what we're measuring to see the effects of the gravity on. So, we don't know what this is going to do at the beginning. These plants may totally die. They may not survive at all. Or they may get huge. Who knows? But the variable that is changed to see how it will affect the dependent variable is called the independent variable. So this is our definition for independent variable. So again, dependent variable, independent variable. The microgravity is the independent variable. So here's our examples. So an example of a dependent variable here is our plant growth in the microgravity experiments. The independent variable is the amount of gravity. Okay, so the microgravity versus normal Earth gravity. That's our independent variable. Scientists on the ISS are using microgravity as an independent variable in other experiments as well, as shown in Figure 4. So there's all kinds of experiments going on in microgravity. Constants. So to be sure they were testing to see how microgravity affects growth, mission specialists kept the other possible factors the same. So a factor that does not change is called a constant. Okay, so that's our constant here, factors that do not change. The microgravity experiments used the same soil type, the same plant type, etc. Additionally, each plant was given the same amount of light and water and was kept at the same temperature. So the type of soil, type of plant, amount of light, amount of water, and temperature were constants in this experiment. So you could actually take all of those as your answer for this. I mean, you got the same thing here as examples. You've got this, but then you got this list here. It's just the same thing. So type of soil, type of plant, amount of light, amount of water, temperature, etc. Why would you do that? Because if I use a different type of plant, it may just get bigger because of that. If there's more, one gets more light, maybe that causes it to grow more. If one gets more water, maybe that causes it to grow more. So you want all these things kept the same, so if you do see a difference, you know it's because of your independent variable. Now, controls. A control is the standard by which the test results can be compared. So after the mission specialists gathered their data on the plants grown in microgravity, they compared their results with the same types of plants grown on Earth's surface with the same constants. In other words, normal Earth gravity is our control here. This comparison allowed them to analyze the data and form a conclusion about whether microgravity has an effect on plant growth. So our control here is, again, normal Earth gravity. Analyze the data. So an important part of every investigation includes recording observations and organizing the test data into easy-to-read tables and graphs. Later in this module, you'll study ways to display data. When you're making and recording observations, you should include all results, even unexpected ones. Many important discoveries have been made from unexpected results. Okay, so why should all results, even unexpected ones, be included in the analysis? Well, many important discoveries have been made from those unexpected results. Also, you want to avoid bias. So if you leave out certain results because they were unexpected, well, then you're basically just including your expected results, which is basically leading to bias. You're basically making the research show what you want it to show or what you thought it should show if you leave out these unexpected results. Okay. Number 18, what are scientific inferences? So scientific inferences are based on observations made using scientific methods. Now, an inference is a conclusion or an explanation. So again, these are conclusions or explanations based on observations made using the scientific methods. Now, all possible scientific explanations must be considered. If the data are not organized in a logical manner, wrong conclusions can be drawn. When a scientist communicates and shares data, other scientists will examine that data, consider how it is analyzed, and compare it to the work of others. So scientists share their data through reports and conferences. In figure 5, a scientist is presenting his data. So we have a guy up here presenting his data from a research project. Draw conclusions. So based on the analysis of the data, the next step is to decide whether the hypothesis is supported. So for the hypothesis to be considered valid and widely accepted, the experiment must result in the same exact data every time it is repeated. If the experiment does not support the hypothesis must be reconsidered. Perhaps the hypothesis needs to be revised, or maybe the experiment's procedures need to be refined. So if we come back over here, number 19, what must happen for a hypothesis to become widely accepted as valid? Well, that hypothesis to be considered widely valid or widely accepted and valid, experiment must result in the same exact data every time it's repeated. Okay, so your answer to number 19 is this. Number 20, what happens if the conclusions of an experiment do not support the original hypothesis? Well, the hypothesis must be reconsidered, or perhaps the hypothesis needs to be revised, or maybe just change the procedures for the experiment. Okay, so that's your answer to number 20. That's your answer to number 19. Now, peer review. Before it is made public, science-based information is reviewed by scientists' peers. These are scientists who work in the same field of study. Peer review is a process by which the procedures and results of an experiment are evaluated by other scientists who are in the same field as those who are conducting similar research. Reviewing other scientists' work is a responsibility that many scientists have. So what is peer review? It's number 21 here. Well, peer review is this here. Process by which procedures and results are examined and evaluated by other scientists. And then 22, what is bias? So scientists also have a responsibility to minimize bias in their investigations. And bias occurs when a scientist's expectations change how the results are analyzed or conclusions are formed. Bias might cause a scientist to select a result from one trial over those from other trials. This is also the reason you include all of your results, even the unexpected ones, because if you eliminate the unexpected results, then that might introduce bias into your results. But an example of bias would be presenting positive test results to promote a product and withholding unfavorable results. So you would report the results that make your product look good, but not the ones that make it look bad. Scientists can reduce bias by running as many trials as possible and by keeping accurate notes of each observation made. Now, this is part of number 23. How can bias be reduced? There's actually a bunch of ways bias can be reduced. One example from up here, when we're talking about positive test results and companies reporting positive test results, you got to look at the money. Who's funding that? So if the company is funding that and they get great results from their product, well, maybe they're biased and they are wanting you to buy their product. So you want funding from parties that aren't interested in the results necessarily. But scientists can reduce bias by running as many trials as possible and by keeping accurate notes of each observation made. Figure 6 shows a scientist who is researching a medication's effectiveness. One way to reduce bias in this case would be to conduct the experiment so that the researchers didn't know which group was the study group and which was the control group. We call this a blind experiment because there's something in medicine called the placebo effect. And if you think you're getting something that's going to make you feel better, like a new medicine or something like that, then you're going to feel better, even if it doesn't really do anything, because mentally you feel better and you report that you feel better. Valid experiments must have data that are measurable. So we want things that are measurable that we can actually get numbers for. For example, a scientist performing a global warming study must base his or her data on accurate measures of global temperatures. And this allows others to compare the results to data they obtain from similar experiments. Most importantly, the experiment must be repeatable. Findings are supportable when scientists around the world perform the same experiment and get the same results. Okay, so those are different ways to reduce bias. Again, you got look where the funding source is coming from, try to get money to fund the experiment from somebody that's not directly involved financially with the results of that experiment. Run many trials, keep accurate notes, use blind experiments where the researchers don't know exactly which group is the study group and which is the control. use measurable data, etc. Okay, so visualizing with models. So our next couple of questions here, what are scientific models? Number 24, and then number 25, why do scientists use models? Well, sometimes scientists cannot see everything they are testing. They might be observing something that is too large or too small, takes too much time to see completely, or happens too quickly to be visible, or doesn't happen frequently enough, or it's hazardous. So any of these things would cause you to use a model. That's actually your answer to number 25. Why do scientists use models? In these cases, scientists use models, and then a model represents an idea, event, or object to help people better understand it. That's your definition for number 24. What are scientific models? Now, models could be a physical model, like you actually build a physical model, like a model car, a model airplane, or something like that. Could also just be a good drawing, a good sketch. It could be a really good description of the event or the idea. It could be mathematical. It could be a computer model. Okay, we talk about computer models down here, but all of those are different types of models. Now, models in history. Models have been used throughout history. Lord Kelvin, a scientist who lived in England in the 1800s, was famous for making models. To model his idea of how light moves through space, he put balls in a bowl of jelly and then encouraged people to move them around with their hands. Recall the models of the atom in Figure 2. Scientists use models of atoms to represent their current understanding because of atoms' small size. High-tech models. So scientific models don't always have to be something you can touch. Another type of model is a computer simulation, like the one shown in Figure 7. It's a flight simulator down here. A computer simulation uses a computer to test a process or procedure and to collect data. Computer software is designed to safely and conveniently mimic the processes under study. Today, many scientists use computers to build models. Okay, so we use computer models like this one here for the flight simulator. So computer simulations, like the ones shown in Figure 7, enable pilots to practice all aspects of flight without ever leaving the ground. So that comes into the too hazardous. You don't want to put somebody in a multi-million-dollar aircraft and they've never really flown one before. In addition, the computer simulation could simulate harsh weather conditions or other in-flight challenges that pilots might face. So this goes back to the doesn't happen frequently enough. How do you practice flying through thunderstorms if you don't have thunderstorms that often? Okay, so use a computer simulation for that. Scientific theories and laws. So our next couple of questions here, what is a scientific theory? Number 26, and then number 27, what is a scientific law? So a scientific theory is an explanation based on knowledge gained from many observations and investigations. It is not a guess. A scientific theory is not a guess. It's something that's been supported by many observations and investigations. Unlike your everyday use of the word theory is really just a guess. Like I have a theory about what's wrong with that, or why that broke or whatever. That's just a guess. But a theory in science is backed up by a lot of observations and investigations. If scientists repeat an investigation and the results always support the hypothesis can be called a theory. As new information becomes available, theories can be modified. It takes a lot to modify a theory, but they are not set in stone. You can modify a theory. So anyway, this is your definition for a scientific theory, which is your answer to number 26. Your answer to number 27, what is a scientific law? Well, that's right here. So a scientific law is a statement about what happens in nature and that always seem. So a scientific law is a statement about what happens in nature and that seems to be true all the time. Laws describe specific relationships under given conditions. They don't explain why or how something happens. Okay, so they don't really explain why it happens. They just say this is what's going to happen. Gravity is an example of a scientific law. If you drop something, it's going to fall to the ground. Objects with mass attract each other. There's a couple of examples of gravity. The law of gravity states that any one mass will attract another mass. We don't necessarily know why or how, we just know it happens. A theory can be used to explain a law, but theories do not become laws. It's not like a hierarchy, like you have hypothesis becomes a theory and then a theory becomes a law. They do different things. Theories explain. So a theory will explain, whereas a law just kind of describes what happens. It says this is going to happen. A theory kind of says this is going to happen because blah, blah, blah. A scientific law doesn't really have that because statement with it. But for example, many theories have been proposed to explain how the law of gravity works, but we haven't really fully accepted any of those. Even so, there are few accepted theories in science and even fewer laws. Now, the limitations of science. So science can help you explain many things, but science cannot explain or solve every question. It is scientists' job to develop hypotheses that can be tested and verified. And again, I said earlier you wanted to add tested to the definition for hypothesis. So hypotheses are, hypotheses can be tested and verified. Questions that cannot be tested and verified, such as those about opinions or values, are not scientific. You might take a survey to gather opinions about a piece of art, such as the painting here in Figure 8, but it would not prove the opinions to be true or false. So some people might think this is a beautiful piece of artwork, and other people may think this is horrible. Neither one of those is really right or wrong. It's a matter of opinion. Okay, so you can't really verify that scientifically. The best you could do is do a survey and decide, yeah, more people think this is ugly than not, or vice versa. Okay, so those are your limitations of science, and that answers number 28. What are some limitations of science?